Thanks for joining us today. I'm John Amond. I'm Professor of Chemistry Emeritus at Montana State University. I'd like to talk with you today about spontaneous electrochemical reactions and how we can order these reactions in terms of an element's ability to gain or steal electrons from another element. Electroplating is a forced electrochemical reaction that's used to plate thin layers of a metal over another metal. Many electron transfer reactions, however, are spontaneous. These take place without you having to do anything to make them go. These can be used for a lot of good. Let's take a look at the garbage can. You've all seen this. Garbage cans don't rust. And here's a garbage can sitting in the snow and it doesn't have rust on it. Why is that? They're made of steel. Normally steel would rust right away. But this garbage can is galvanized. It's covered with zinc. What goes on there? The iron and zinc both exist as ions and as metal. And in the case of the metallic iron, it can give up electrons going left to become iron 2. The iron 2 can gain electrons to become iron 0. Likewise, the zinc can move to the left, giving up electrons to become zinc plus 2, and it can go to the right to become zinc 0. Both of these reactions are possible when the materials are sitting there. What is going on is that the iron has a greater attraction for electrons than zinc, and if the iron is oxidized, it will immediately take electrons from the zinc, and that pushes the zinc reaction, the lower one, to the left, and it pushes the iron reaction to the right. And as long as there's any zinc there, you can't have any zinc ion. I have here an electrochemical half-cell module. This has 8 little cylinders in it, and these will hold about 3 milliliters of an ion solution. They connect through a little channel here to a porous plastic sleeve, and we put potassium nitrate in the middle for a salt bridge. So these can be coupled by motion of ions through that liquid, but the ions won't move very fast because of this porous cup. I'm going to set this down. I'm going to put a strip of tin in this one. I'm going to put a strip of copper in this one. And then I'm going to put a strip of zinc in this one. And I'm going to connect a black lead from the voltmeter to the zinc electrode. And then I'm going to break for just a second and put some tin ion in this one, some copper ion solution in this one, and some zinc ion solution in this one. This will give us both the metal and the ion of the metal. Okay, let me start out by choosing a reference. I'm going to use tin. I'll click that here. I'll connect the negative or black lead of the voltmeter to the tin, and then I'm going to use copper as my first sample because that's all set up. I'll click copper and we'll connect it, and when I do, the voltmeter reads, and let's see what's going on here. Electrons are flowing from the reference cell, the tin, through a light bulb to show that it's running, out to the copper half cell. Voltage is 0.461 volts. And what's going on then is there's oxidation taking place on the tin side, reduction on the copper side. Copper is stealing electrons from the tin, and I've got a 0.461 volt here. If I accept that, it says copper is above the tin on the ability to gain electron scale. Let's try another metal. Let's try zinc. Okay. Let's click zinc as our sample, and I'll connect it, and when I connect it, the electrons are running the other direction. They're coming from the zinc in the red connection, out the black, to the tin. Tin is taking electrons from the zinc, and if I click accept here, it says zinc is below tin on the electron attracting ability scale. Let's try another element. Let's try iron. And I will click the iron as our sample, and we'll connect it up. And it says minus 0.305. It says electrons are running from the iron to the tin. And if I accept that, it says iron is below tin in the ability to gain electron scale. Zinc is lower yet, copper is above it. Let's try another element. Let's try silver. Okay, I'll click silver as our sample, and I'll connect it up, and it says 0.92, and this time the electrons are running from the tin to the silver, and so silver has a greater electron attracting ability than tin. I'll accept that value, and it shows up here on the top of our scale. I have one more piece of metal here. I have aluminum, so let's give that a try. And I'll click aluminum as our sample, tin is still our reference. Let me connect it, and it says minus 1.53. Electrons are running this direction. Aluminum is giving up electrons to tin, and so let's accept that. And I have here now a scale we've built that has 6 elements on it in terms of ability to gain electrons. The silver, electrons from anything on the scale below it. Aluminum will give up electrons to anything above it. And in between we have zinc, iron, tin, and copper. One of the things you might consider here is that silver is often used for jewelry and for tableware. It has a great attraction for electrons, doesn't give them up very easily at all, and so it doesn't oxidize rapidly. Zinc loses electrons rapidly, aluminum very rapidly, and so we have a scale here called the Electrochemical Series. It shows elements in order of their ability to gain electrons.